This is what you will see after downloading a trial version of the SP frame, or you can just, as I said before, try to get a version from one of your friends to work out the project. And remember that it's valid for 14 days, so that if you didn't get a chance to work out your project within the 14 days, you will lose the accessibility to it. So as you see, it's a typical project. It does have ribbon, that does have file, access defined, process, analyze, show, and other things. You still can import projects from outside. It takes DXF, and that is the common one for the AutoCAD. You can save your file as DXF, but I really do not recommend having saving your file as AutoCAD and then import it here, because sometimes you see that compatibility problems happen, and then if the joints that you are making are not close enough and they are not attached to each other, the project will keep telling you errors, and you will struggle to find where is that error unless your project is just connected well and everything is fine, and the importing process is okay. But you still can do it here. It's not a problem. So of course you have here open save as, and other things. But here is the important thing. You have first of all define the units, because you have the metric and the imperial units. So that once you hit the metric, you see that the length is in millimeters, and you can adjust these. I always prefer to work out with meters. The area maybe meter square or whatever. It's fine. The point load is in newton, so that if you decide to make newtons or you shift to kilonewton, always remember that. Then the moment load is in kilonewton meter. This is what I prefer to work with. If you decide to work with other things, do it according to your understanding or according to your convenience. So this is the units. I defined it here, and just this instead of millimeters or something like that. But pay attention that you don't use the metric and the imperial unit, because we stick to our metric system. After that, you define the units. You need to define what is the type that you're working with. And you have here 4 items: either 2D frame, 3D frame, 2D truss, 3D truss. And the difference we showed that several times. The difference is obvious. If you 2D and 3D is very obvious. 2D is working in a plane, 3D is working in a 3D. But the frame has the truss. Let me start with the truss. The truss always have the forces developed in it as axial forces only. However, the frame might have shear force and might have moments induced in their members. So that once you analyze the members of the truss, you will see either tension or compression, and that's it, because it's axial force. However, the frame might be complicated a little because it deals with 3 internal forces at the same time. So that here you define, of course, I will do here a problem with 2D truss, but in your project, you'll do 3D truss because you have to deal with a 3D. But the essence is the same. Because of the timing, I want to just show you the features. This is a 2D truss, and you can type here the project that you have and other things. So that I define my type, and then after that, there is an item here that says defaults, and these are the modulus of elasticity. I hope that you still remember these: the density of the structure, the area of each member, and the moment of inertia. These are the important things that we have. And of course, the software accounts also for thermal coefficients if there is expansion or contraction happening in these members, because it will affect the node displacement at the end. But we don't want to worry about these. But these are what you also want to work with if you want to define your area and define your moment of inertia. Because if you are doing a truss from steel, you have to define your moment of inertia is calculated, but the modulus of elasticity of the steel, you have to define it. And these are fixed number for the elasticity for the steel, and the section area as well. You can define what cross section you want to work with, and that will vary from one to the other. And after you define your units, you go to process joints, and that is the important part. Process joints, and it gives you here what is the X, Y, and Z. You see Z is locked because we are dealing with 2D truss. If it's 3D, the Z will be enabled for you, and then you can define what are the coordinates and give it labels. So that if you are making labels, and I prefer to have it ABC because 1 to 3 is going to be confusing with the numbers afterwards. So that give label for your X, Y coordinates for each member. So that if we want to do maybe a simple problem like this that we already solved. These are 6 points, and we need to give each one of them X and Y. And pay attention that always remember to do your whole system in one quadrant, so that avoid having negatives in your coordinates. So that do not give 0 and 0 and then negative 5 and 0 and 5 and 5. So that always make your reference point, which is 0 and 0, in one quadrant, so that it's going to be the very end point, which is for our case point A here, because everything else will be in quadrant 1. If you are dealing also with 3D, make sure that the edge of your structure is 0 and 0, and then you go into one quadrant. Do not pick a point that is in the middle of the structure and refer to it as 0 and 0, so that your points will be scattered between negatives and positive, because this will mess up the calculation. That is so important. Always remember that. And we can define our structure, our joints, because we have the first point 0, 0, the second point B is going to be 4 and 0, and then the C is going to be 8 and 0. I give them here just quadrants, coordinates. So I define my A 0 and 0, and I have to add, because if I don't see here in the list the point, it's not created for me. And then I go to point B, it's 4 and 0, and add, and then point C, it's 8, add, and then shifting to the upper ones, I'm going to have 0 and 4, and 4 and 4, and 8 and 4.
0 and 3.
0 and the height was 3?
Yes, 3.
Yes, 0 and 3, thank you. So that is going to be 0 and 3, and do not forget to give it another label, because you will overwrite if you pick the same point. So this is D, and where the A, B, C, D, E? Yes, no, it's D, F, it's opposite. So that D, I can come here and give that Y is 3 and 8, and add, request name, so that you have to hit down the 5, and once you hit down the 5, it's going to be 8 and 3. That is the point, and then E is going to be 4 and 3, add, F is going to be 0 and 3, and then add. So here I define all the points. I do not see it here, so that I have to show, and then preferences. Here, it gives me what you want to show, so that I want to see the joints with label, not square, so that I want to see where is A, B, C, D, and also I want to see the members and the fixed Ds. So that these are the points, as you see here, it's very tiny a little bit, but it's A, B, C, D, E, F, so that we do not miss any of the location of the coordinates. And then after that, you go to process members, and you want to now see, after developing the joints, these open up for you. It was locked up because you cannot make fixed Ds or any members without having the joints first. So the first step is to make the joints and then go to the members. Which one is connected to which one? So that we have A connected to B, and then add, and it's label 1, it's fine, and then B connected to C, then add, and then we have C connected to D, and then add, and we have D connected to E, add, and then E connected to F, add, and then A connected to F, add. These are the outer box, and then we have B connected to E, add, and then we have the diagonals, A connected to E. If I'm doing a mistake, let me know, because I'm getting old, I can't see numbers perfectly. B and letters, B connected to F, add, and then B connected to D, add, and then C connected to E, add. Okay, so that here we created the members, and that is similar to what we have exactly in our problem. And then after that, we have to make the fixed Ds. What are the supports? How the supports are there? Here is the list of the joints that you have A to F, and our problem is just having, you remember this, a number at F is a reaction. It's already calculated for us, but technically the problem shouldn't have the action at F or at C, because these are the points here, the connections, the supports, and F and C will have the supports, and then D and A have the load, external load. So that we will not put 20 and 10 here. We'll let the program calculate it for us. Hopefully it will calculate correct, and it should for sure. So that we come to F. and we'll say what is the condition that F has. F is well, it's simply supported. It's not clear for us which one is roller and which one is spin, but we can decide on that because since we have all of the forces vertical, we won't have any lateral forces because of the Fx is going to be equal to 0 and you won't have any lateral forces. So definitely the reaction at the x is going to be equal to 0 at either point. So pay attention here. I'm building an indeterminate truss. It's not determinate, but the software will calculate it for me. It's not gonna simplify it. It will give me the exact solutions. So I will say at F, what is the fixed is? Means that dx, if I hit dx and dy, that means it's spin connection, so that the member is not allowed to move at x or y at this point. So that I add here, and the other element is at c, and I'll give it just roller, so that means that it's allowed to move in the x, but it's not allowed to move in the y. And then I will add. And then when I hit OK, I see that. You see that at F, you see this little line ended or capped with another dash here, means that it's restricted to move in x and y. Whereas at the other joint, it says just in that y, it's forbidden to move, but it is allowed to slide in the x. And that is my conditions for the process of the fixed keys. After that, I will go to define my load case. Where is the forces? I need to produce the forces or generate the forces. So define load. Yes, define load case. And you see here self is coming from the. Let me show you here. It's coming from the defaults that you set. What is the default? So that because you specify an area and you specify a length, it will calculate the loads for you, and that is the self. We will ignore this because we are not included in our case. But if you want to include it, you still can do it as self here. But I will introduce my I would say point, and that is the loads that are applied at the loads. Always remember that in the truss you apply your forces at the joints. You don't apply it in the middle. And I will hit OK and OK. After that, I will go to analyze the joint loads. Analyze joint loads. So what is there? It also gives me the joints only because it's going to be applied at the joints. In the frame, it's not going to be like this. In the frame, you can apply the load along any length of any portion of the frame, so that it will give you the joint and it will give you another window to tell you how far from this joint you want to apply the load, so that I can come to A and say at 2 meters, so that it will count 2 meters and then apply the load at this location. That is the frame, but for the joint, it's not going to be applicable. And here also you have to make sure that the points load that you picked and created in the define is going to be shown up here. So this is a load case. If I will set some combination of forces, I might create another case and set another combination of forces and analyze the truss, my truss using this kind set of forces and the other set of forces separately from each other. So at here, what is going to happen is that I have 10 going down and 20 going down at A and B. So that I come at A and I have, and I hope that I'm respecting the units here. Yeah, it's kilonewton, that is good. So that at Fx, nothing is happening, but at Fy, there is 10. And do not forget that it's pointing down, so I give it a negative value. Minus 10 kilonewton. Remember here that there is no moment applied because that is a truss. If it's a frame, it will give you here also points to apply as moment in here. So we hit that, and we come to point B, and we say that it's negative 20, and add, and then okay. These forces still not shown to us. So we have to go to show, and then load diagrams, point load, that is point load. And if we have distributed load, it will show it also to us, but we don't have distributed load here, so no need to show or click this. But pay attention, here's a factor. It tells us because if the forces is too small, it will not show properly. You can magnify those, but this is just for graphical representation. So that if I say 2, it doesn't multiply the force by 2. It's just showing graphically here as magnified. But let me click here. You see that those little arrows that are pointing down here, this one and that one, are shown at A and B. And if we just see here, see that arrow? If we, yes.
Doctor, is there a way to active the dimensions? Or no?
Active the dimension?
Yeah, like it can show me.
Oh, the dimensions on the the label is there. I don't think there is. You can go to the item at the end and it will show you in the table. But in the graphics, in the interface, I do not think there is a way to show the dimensions. But however, if you go to member info, you will find the length of it here, which joint is connected to, and what is the where it's connected from one to what, and what is the section. Give you some ideas about that. But on the graphics, it will not show the dimension for you for the on the graphics. Right. Thank you for this. Right. We have now created the load, and now we have to select analyze, and we have to select what is the load combination we want to select. Because as I said to you here, here is the self that was default, and this is the point load, and we have to have it included in the vector case and then add. I might add another force if I want, so that you can create a set of maybe vertical forces that represent the gravitational forces, and you might create also lateral forces that represent your wind load. And see here, if I included an add now, it will analyze both of them for me. But let's not overcomplicate things. I want to just have my point load included. And then just deal with my point load here. Once I hit OK, now I'm ready to analyze my truss. So you go to analyze and then solve. If you did not get successfully at the end, that means you're having a problem. Here you have successfully calculated, successfully. You might get sometimes error, and that is because of one important thing is that you might make unstable system. What does it mean? It means that your structure is not stable. It means that you're not providing enough fixed connections, and the forces will slide your truss, will make move, and that is not a stable structure, and that is why it will give you error in here. So that this is it, and then once you run it, and then you have the diagrams in ready, and then you can check the let's see here. Okay, so here let's see. I want to see the there is the member results here, but I want to see the where diagrams. Okay, that is the so that I want to see here the let's see the result diagram. So here true shape and deformed shape. And if I hit this is my truss after deformation. So the original one was the green, and then the deformation having it like this. Pay attention these elements, the fixed connections or the pin connection that is at point F and C is not allowing the truss to move at all. However, we have some displacement at the mid of the truss at point B, and of course at point E tremendously. And since also the left corner of D, let me show it here. This one at D, it's allowed to move. That's why it translates from to the left and down, because the nature of the forces are pushing the truss down. That is something you have to examine. You have to experience this. Does that make sense, or you are getting some weird results? And because we have our forces are pushing the truss downwards, both of them, we see that the truss is pushed down at point B. And as you see, the more or the freer the points, the more the forces or the more the displacement you will see. And you see that it moved a lot at B, and since this is fixed, it doesn't move, and not fixed, but it's a connection, pin connection or roller connection that does not allow it to move. And at the same time here, it's not allowing it to move as well. So this is the result that we would see. And also we can go to analyze and see the joint results. So this is the displacement. It tells you each point, and you can have them differently shown for you here, but it tells you at each point how much it displaced. Each point how much it displaced, as you see here. Now see the F is not allowed to move, and it's almost zeros, and the other one is almost zeros as well because it's to the 33, so that it's not allowed to move. Also see here zero, and that is the second column in dy is zeros almost because it's multiplied to negative 33, and that is zero. And the C as well, the vertical component of the reactions dy is almost also a zero because it is not allowed to. This is the joint displacement. I can go to end forces, and it tells me how the forces at each location is also applied. I want to show you here, analyze. Let's go to the support reactions. Analyze support reactions. See, this is F and C. So F is 20 and C is 10, and that is what we have. And pay attention that this is in kilonewton. So that the forces in the member. So that if I open up the member result, and here is the notation for the elements. So that member 1, member 2, member 3 gives me here what 2 up to the members that I have. I have here 11 members, and the load combination is there, and it asks me what is the shear. Of course, the shear is zero because these members are not exposed to any internal forces. However, if I go and of course the moment also is going to be zero. And you see here, whoever I think high or tiny, the length. This is the length of the member number 1. It's 4 meters, and you see the axial force is what we are want to have. But then we go to define. We set the units, and now we need to shift to the 3D truss. And then okay, and the defaults are things that you can define as well. And then we go to process joints. Now we have A, and then for D we have 800. Building those, and for E, hopefully we did not make a mistake. E is 480, and then that. So that I build A, B, C, D, E, okay, and then I go to show references. I want to see the joints in label, member labels, and fix these, okay, so that I have here C and those. But since it's coming from the Z, you will see the elements like this, so that it's in the plane XY. If you are standing in plane XY, you would see 3 points. You would see A and D and E, and then the rest B and C are mapped on top of it. That's why you cannot see, or the other way around. You see the top 2 points, the lower points are not shown in here. But let's process the joints. Let's process the members. What is the process? Define that members, so that we have A connected to B, add, and then B connected to C, add, and C connected to D, add, and A connected to D, add, and we have also A connected to C, and then we build the outer or the left box with the diagonal. We need to E is connected to all of the point. So E, A, E, B, E, C, E, D, E. All of them are we connect to A, E, add, B, E, add, C, D, C, D, add, D, E, add, and then hit OK. You see that? Of course, you can adjust the 3D so that we can go to rotate and say that it's not allowed to move with X. And remember here, this now is activated for us, the DZ, and we hit the A, we hit the S, and then we go to the second point, which is B. Here it's not allowed to move in Y and X, so that B not allowed to move in Y and X, and then add, and C is not allowed to move, I guess, in one of those, which is X or Y. It's Y, and then add. Let's see, just verify. Here it's not allowed to move in Y, so that these are reactions that we have, and add, and then OK. You see it, so that I am seeing the 2 here, and then I'm seeing 3 here, and I'm seeing 1 there. So this is the 3 fixes I just have, and then I have to go to load cases, and then add. I will make also point loads. Add, okay, and then go to process. Then we go to analyze joint loads. What's happening? We have external loads here. We have just 600 at E, but it's pointing down, and that is inbound, by the way. I did the problem in metric system, but it's fine. We still can do it with. I don't think it will just give us also, but I will keep it 600. So this is A, and what's happening? X and Y and Z. It's going along the Z in the negative direction. So it is negative 600. And pay attention here. I'm drawing it with kilonewton. However, the problem is in pound and foot, pound and yes, and foot. So this is our. We have to add. Do not forget to add, because if you type it here and hit OK, it won't show us anything, any force. And then OK, and then we have to go to show load diagrams, point load. If I did this, and OK, I see that it's running. Did we do it wrong? Define process, joint members, define process, analyze joint loads. Yeah, we put it at A, and that is something handy because we have to see it. We have to read this, and we come to E, and then do the same thing here and add. Okay, so that the force is shifted to E, as you see in here. Now we have the last point before the analysis. We have to go to load combination and select my point load, and then add, and then OK, and then analyze and solve, and then solve. You have to see this successfully finished, and you go to. I want to see first. Let's see here, member results. This is the member results. I want to see the load diagrams. This is the load. I want to see the result diagram. Show deformed true shape, and if the deflection is too small, you can still, I think, magnify it by a factor here. You can see that the factor here. This is going to show you the original ones, as you see that this is the original of the shapes, and then what happened, as you see here at point A, it's completely forbidden to move. That's why it's fixed at point A. However, the movement at E was huge because of the force existence and the free nature of this point. It moved a lot. You see, this is the original, and now it moved to this location. If you, after finishing this is the almost what is needed for reviewing the project, and then you go to analyze and see the support reactions. And you see here 366 in A, and then 36 in B, and then 6.8, which is almost 0 at C. So this is C 0, and then you have those. If I go to my here, you have the 600 and the 300 and the 300, 600, 600 at AX and B, X, 3, and 6. So these are the numbers, and the rest is going to be equal to zeros because C here is not showing anything. And then if you go to analyze and then member results and specify the members, let's go to, I think, 1. And we take the axial force, you see that it's 600 kilonewton happening in it as internal forces. Hopefully, you didn't do anything mistakenly. So that at member AB, I want to just, yes, BAE, you see it, and the bottom is 600. But I have it in kilonewton. I feed the numbers in kilonewton so that it should be in kilonewton, but it's 600. If I go to member 4, for instance, let's go to member 4, you see it's 0, 0 and 0, and that was, I think, what we have in member 4, which was AD. Let's see what is AD. Yes, it's 0 here. Let's check AE, 670.8. AE, we go to, it's AE, which is member, is this 6 or 8? I think it's 6. So that we go to 6, and it's 6.7. So these are the numbers, and here because we here solved a 3D problem with exact solutions, so that it's determinate problem, it's not indeterminate. So that technically, what the method that we are having by summing the forces in x and y and z and finding the internal forces, we get typical results compared to the problem that we have. Whereas